Hey guys, this is the first of a two-part video on the ideal gas laws and a bunch of applications of them. So we're going to start with the big picture first and sort of see the end game that we all know. Plus, you've already seen the ideal gas law probably in chemistry. And then we'll go and look sort of how we got to the ideal gas law, not as like a history lesson, but because those individual examples that combine together to make the ideal gas law are examples that they often use in AP problems still. So let's say this. We've got a container of gas right here, right? And there's little molecules flying all around. Now, long before we knew that there was little molecules of gas flying all around, people actually started studying the properties of gas. So let's start looking first at some macro gas variables. So like the big stuff that we would notice right away. So one thing that we're going to focus on a lot is the pressure of that gas. And we'll tend to measure that in pascals, or you'll often see kilopascals because that's not that much pressure. Or you could see an ATM. You tend to use ATM more in chemistry. We'll typically use pascals here. Another variable of the gas that we could look at, a big macro variable, is the volume. And in physics, we tend to measure it in cubic meters. In chemistry, you tend to do it in liters, or you could, do it in cubic centimeters, which is the same thing as a milliliter, but we'll tend to use cubic meters. We will look at the temperature of the gas, and we will measure that in Kelvin. More on that later. And then, temperature, I'm gonna take you out here for a second so there's room. We could also look at the amount of the gas, and by amount we mean how many particles. And so we could actually count the number of particles, or we'll often use a mole. So we'll count by kind of like a dozen, but in this case like 6.023 times 10 to the 23rd. So those are the big things that we're looking at, the big macro things: pressure, volume, amount, and temperature there. And people knew about all of those four things before they started to come up with what was causing them. So let's talk now about what is causing them. And this is part of what Ludwig Boltzmann and others were arguing with their kinetic theory of gases. So what are the micro causes of these things? Well, first of all, let's talk about what is causing the pressure. So the collisions between these little molecules that are zipping around, hitting the walls, it's the collision between these particles and walls that cause pressure. So it all has to do, everything we want to frame this in terms of causes is the collisions of these particles with the wall there. So what will cause those collisions to exert more force and therefore more pressure? Well, one thing we can look at is the more frequent the collisions, the greater the pressure. So if these guys are hitting the walls more often, then they will cause more pressure. Well, what are some ways we could cause them to hit more often? We could make them go faster, right? Or we can make the container smaller. If you imagine you guys are like blindfolded and wandering around a room, and how often do you hit the wall? Well, one way we could do it is to put more of you in there, right? That would cause you to hit the walls more frequently. We could make you guys move faster, right? If you move faster, you'd hit the walls more frequently. Or we could make the room smaller, like as opposed if you were in the gym versus like room 151, you would hit the walls more frequently. So the more frequent the collisions, the greater the pressure will be. And then there's another thing, which is essentially, if you're trying to explain it to someone without a lot of physics terminology, like the harder the hit, the more pressure there'll be. So there's two ways to get a harder hit. The greater the speed that the particles hit the wall, the greater the pressure. And we think of this as related to temperature, which it is, but it's not the whole picture, because also the greater the mass, the greater the pressure. So these two things together sort of give us the kinetic energy, right? So basically the way you want to think about it is the more kinetic energy they hit the wall with, then the more pressure they're going to exert on the wall. So the faster they move, the heavier they move, the more there are, the smaller the container. All of those things will cause more collisions and therefore more pressure in that case. So let's talk about, we're going to have four different gas laws we're going to look at in a second. But all four of these gas laws are going to combine to give us the ideal gas law. I'm going to move this out of here for now so we have a bit more space. I'll move this over here. So the ideal gas law typically looks like this. So PV equals nRT. PivNert you've probably learned from chemistry class. So this is pressure that we talked about, volume that we talked about, T is temperature that we talked about, and this little n right there, that is the number of moles. So that's one way of counting the amount. And in this equation here, the R right here is a constant. It's called the universal gas constant, and it's 8.31 joules per Kelvin per mole. Don't worry about all of that, it just makes the number come out. If you forget this number, that's okay, because it's on your equation sheet there. Now, this is one version of it that you'll see on your constant sheet. There is another version that you'll see as well. And that version looks very similar, but like this. PV equals capital N kBT. So when you use this version, what's everything mean? Well, the capital N stands for the number of molecules, or atoms, but it's typically always a molecule, because even oxygen will become a diatomic molecule. So this is the number of molecules, and then we've already seen this before. So the Kb is Boltzmann's constant, which is 1.38 times 10 to the 23rd joules per Kelvin. A crazy coincidence, I'm trying to say, of the universe is, look, these two different constants get reversed. I just noticed 8.31 and 1.38. Anyway, there's no reason for that. Don't be like, oh my gosh, why is that? It's just coincidence. So that is the that is the ideal gas law. Now, what is an ideal gas? That's the last thing we want to say in this video before we move on to the other one. So an ideal gas is kind of like saying, like, no friction or free fall. Like, we can rarely actually get it to perfectly happen, but lots of cases are close enough. So the first thing we want to look at, which makes an ideal gas, is all the collisions are perfectly elastic. And if you remember from AP1, what perfectly elastic means is there's no loss of kinetic energy when there's a collision. That's both between the particles and each other, and the particles in the wall there. Both those types of collisions are considered perfectly elastic. Another condition is that there are no intermolecular forces in an ideal gas. So these guys aren't really pulling on each other or trying to bind to each other much at all. And then the last one here is that the molecules take up basically no space, especially in comparison to the size of the container. And for small gases, even oxygen, compared to hydrogen, but a little diatomic oxygen molecule doesn't take up much space there at all. So that's sort of the big picture, what we're going to lead to. And then we'll go and look now at the individual gas laws, how they combine to give us the ideal gas law, and how they give us very specific examples to look at.